Hello, my name is Michael Glinsky. The beginning part of this work with the application of the MST was done by my consulting company, QI Tech Consulting, under contract with Sandia National Laboratories. The latter part of the work with the Wavelet Phase Harmonics, as well as the understanding of what was going on, was developed after the project was complete. This work was done in conjunction with Catherine Maupin from Sandia National Laboratories. If you would like to go and find out more about this project and also more about the things that I have done, just click on the QI Tech link and go to Publications. For instance, to go and find the video for this presentation, that you just go and click here on the YouTube link, as well as the PDF of the presentation and the preprint for the research. This work uses machine and deep learning to form a surrogate for the fields that come out of resistive 2D MHD liner implosions using the Mallat Scattering Transformation and a relative of it. If you would like to get access to the preprint, that all you have to do of the paper on this work that is going to appear in Computational Mechanics, all you have to do is click on the title, and that will take you to the preprint for you to read and download. Here is the MagLIF geometry that was simulated. One has a beryllium liner with the deuterium gas inside of it. There's initially an axial magnetic field of size BZ0, and then a large current is driven axially through the liner of maximum size IZ0. That this current causes a large external azimuthal field, which goes and compresses the liner and the gas, more importantly, the gas inside. The liner is of width small w, average radius r0, inner radius r inner, and outer radius r outer. The density of the gas is little n0, and the temperature is T0. There is a azimuthal perturbation put on the liner of size delta I to the inner surface, delta O for the outer surface, as a function of the azimuthal angle phi. The Mallat Scattering Transformations will be displayed as both first and second order, as would be a Fourier 2D to Fourier transform, where the axis is the scale of the transform, and that is going to be either linear or logarithmic, and that will be indicated at the proper time, and the azimuth of the transformation is indicated by the sector that it is posted in. For the second order transformation, the radius again is proportional to the scale of the transformation. The major sector azimuthally is indicative of the angle of the first order transformation, and the angle of the second order transformation is going to be indicated in terms of the subdivision. That the transformation is not orthogonal in azimuth, and because of that, it is overdetermined and redundant. and that also because of it, this particular posting, because they are not over posting values, will change dramatically with the resolution. As you increase the resolution, is not simply a higher resolution version. You'll see that you will get more sectors around here, but then get the same number of inner oscillations associated with it. This slide shows an example of the evolution of the liner on the left-hand side, the gas in the middle, and a blow-up of the gas on the right-hand side. If you're looking at a PDF of this presentation, you only need to click on the title to this slide to take you to a YouTube video of the animation that I'm going to be showing you. You now see in the gas the shock of the start of the implosion bounce in and out. You also see on the left-hand side the implosion start on the outside of the liner and the shock and the being driven in. You see a relatively symmetric implosion that becomes asymmetric right near the maximum stagnation and then goes and expands back out in this dipole character. I've now started the animation of the zoom in. You see it come in symmetrically, go asymmetric into an M=2 dumbbell mode, and then go out. And that in general, then when you're at this point of maximum stagnation, that's called bang time or T-bang. We ended up going and forming up a training ensemble by doing an ensemble of these simulations that you just saw, that the control parameters are the adiabat, or which is determined by the preheat or the initial temperature that was sampled logarithmically between a value of 10 volts up to 630 volts. That normally you consider it a higher adiabat. The lower the temperature, the more compression that you end up getting, and also the more opportunity in order to develop and enhance the instability. And that's one reason why this is chosen as one of the important control parameters. The second important control parameter is the liner aspect ratio. That was sampled linearly between 3 and 9, which corresponds to thicknesses between 800 down to 266 microns. The higher the liner aspect ratio, the higher the acceleration and the higher the linear growth rate of the magnetic Rayleigh-Taylor instability. And that is again why this was chosen to be one of the critical control parameters of the simulations. The output fields were sampled between 0 to 200 milliseconds, which is the pulse length. And it was sampled equally spaced by 2.5 nanoseconds. The randomly sampled stochastic parameters were the magnitude of the liner perturbation, which was sampled logarithmically from 1% to 2% of the thickness, as well as the phase of the M=2, 3, and 4 azimuthal perturbations. They were sampled uniformly. The constant parameters are the liner radius, the initial axial magnetic field, the initial D2 gas density, and the maximum axial current at the values shown here, which are characteristic of the current MagLIF design point. The dependent field parameters that ended up being sampled were the liner density at a resolution of 10 microns in terms of X and Y, and the previous indicated time resolution, as well as the magnetic field. So therefore, that we ended up forming and doing 539 simulations that was sampled at 81 times with 2 outputs that ended up giving about 90,000 images, which were downsampled to 256 by 256 from approximately 700 by 700. This took 200 core hours on the Livermore supercomputer, and that wall clock using about 2,400 chords or 60 nodes that took about a week of computation. That 227 of these samples were Latin hypercube sampled in terms of the log of T naught, the aspect ratio, and the log of the liner perturbation, and uniformly in the phase angles of the perturbation. In addition, there were 512 uniform samples that in terms of all the parameters that were sampled over. This slide goes and shows the characteristics of the distribution, that what is shown on the left-hand side will be the initial liner perturbation for each realization, as well as the first and second order Mallat Scattering Transformation of that. Also, what the liner looked like for that simulation 12.5 nanoseconds before bang time or stagnation, as well as the about 25 nanoseconds after the bang time. On the right, I will go and show you the evolution for the thickest to the thinnest liner. And over time, you want to note that the thinner liner goes and converges faster and sooner. And to see these movies, if you're viewing from the PDF, as with the previous slide, just click on the title to this slide. That will take you to YouTube, where you can go and see this animation. Now I am showing you the variation from realization to realization, as well as the changes in the Mallat scattering coefficients. This is a linear scale for the MST. I'm now starting the implosion simulations on the right. Again, notice that the thinnest liner goes and has more acceleration, converges more quickly to a and then finally at the end of these movies will be displayed the color maps. Here is the guts of the work that was done for Sandia National Laboratories under contract, and that in terms of forming the surrogate using the MST. I call your attention over here to the right, where we start with the image of the liner density. The log base 10 was taken of that. Subsequent to that, the Mallat scattering transformation was taken. The logarithm was taken of the Mallat scattering coefficient. The mean Mallat scattering pattern transformation was over the ensemble was subtracted from them for display purposes to take out this dominant pattern in the MST. This was also taken out otherwise in the principal components analysis. This is linear in scale in terms of the radius, where the principal components shown here are logarithmic in that. A PCA was taken, 7 components were retained. There are some physics reasons why the number 7 was chosen, but that also ended up having 94% of the variance explained in the 7 principal components. A surrogate for the 7 principal components was formed given the Z transform values of the temperature, aspect ratio, time, the amount, the size of the liner perturbation, as well as the initial angles. The best results by far came using a multi-layer perceptron with ReLU activation. The optimum structure was this decoder encoder format of 25, 15, and 25 hidden layers. At the end of the talk, I'll be telling you why this form was used and why the architecture of this was chosen, especially the number 15 and about and also I searched around in terms of what the outer layers should be, but the first thing that I tried ended up being the best in this case. There was very good performance, and that will be shown by the evolution of each of the principal components in time compared to the actual, which is the dim one, and all where the simulated will be the bold. A permutation feature importance analysis was done and analyzed also. Also to the right, there was an analysis I'll explain in detail to be able to identify which principal component was predominantly associated with which of the input parameters. The linear correlation coefficient of the predicted versus actual are shown next to each principal component. These range from about a high of 97% to a low of 57%, with the average correlation of all the components being a very acceptable 81%. Here is more detail on the principal component analysis. Each of the principal components, MSTs, are shown with a linear radial scale here, and the overall color maps are shown on the lower right-hand side with the identification of each of these principal components, which I'll explain on the next 2 slides to the left of it. In the upper left-hand corner is the mean MST over the ensemble, the explained variance of each one of the principal components, as well as the integral of that curve. And the lower left-hand corner is the scatter diagrams associated with each one of each pair of the input parameters, as well as the distribution in each one of the input parameters shown along the diagonal. In order to identify each one of the principal components, first a singular value decomposition was done of the cross correlation of the input parameters to the MSTs. What is shown here are the singular vectors in terms of the input parameters on the left and the MST on the right. you can go and see that, first of all, that the principal component analysis goes and more quickly captures in fewer principal components the variation than the singular value decomposition. But the singular value decomposition of the cross correlation that we've done now goes and shows that that it tends to be only one of the input parameters that dominates and it's a unique one for each one of the singular valued singular value decompositions, and so that we now know what the MST looks like for each one of these, and that we can now go and label each one of these components with the input parameter that it predominantly represents. Now, to go and relate this back to the principal components, a singular value decomposition of the correlation of the principal components to this singular value decomposition was given. The singular values vectors in terms of this previous singular value decomposition are shown in black on the top, and in terms of the principal components in green on the bottom. We obviously have labeled the previous singular vectors associated with the input parameters that is determined on the previous slide. And so now you can go and read off that the first principal component is time, the second principal component is delta liner, the third principal component is preheat, etc. And that's how we ended up getting what the labels were. First of all, a shallow machine learnings were tried. The best of these was a support vector regression using a radial basis, that a grid search was done for both the best regularization as well as the size of the radial basis function, that it was found that the best point was found here, but the regularization was increased so that we sort of maximized the regularization to reduce the amount of overtraining or potential overfitting in the regression. That the predicted versus actual scatter plots are shown here, both nonlinear curvature as well as sort of multiple branches are shown, which are pathologies in the fit. Also, the correlation coefficients range from a high of a acceptable value of about 90% down to a totally unacceptable value of 11 and 10%. The overall best value is 46% on average. What is shown over here on the right are the predicted versus actual amounts of each one of the principal component vectors. And you can see that the stagnation, the high frequency, is not captured. It's a very low frequency representation of that. The regularization can be, or the size of the kernel can be decreased enough to be able to capture these stagnations, but those results did not cross-validate. So we ended up going to this multi-layer perceptron with ReLU activation. Different structures of the hidden layers were sampled over, and as well as the amount of the regularization alpha. What was used was the first guess, which was 25, 15, 25. And also we ended up increasing the amount of regularization in order to decrease the amount of potential overfitting in the regression. You can see that there is no pathologies in terms of nonlinear or multiple branches on any of the predicted versus actual scatter plots. And again, they range from a high of a correlation coefficient of 97% down to a low of 57%. What is more important, all of the details of the evolution of the principal components here on the right are captured, especially the point of stagnation or bang time and the cusp associated with it. And on the lower right here, that you can go and see the permutation feature importance analysis. These results will be discussed in more detail on a couple slides to come. Now, quite a bit can be learned by studying the form and the evolution of the wavelet phase harmonics, but for many purposes, you would like to go and have a surrogate of what the liner density and magnetic field itself would go. Unfortunately, the MST only goes and has the magnitude of the transformation. It does not have the complex phase of the transformation. There is a flawed but not too bad version of this called the Mallat Scattering Transformation that goes and is called Wavelet Phase Harmonics. The flaws of it are discussed in much more detail in the preprint paper written on this, but basically it does go and include the phase, even though it's highly redundant. And so a gradient search needs to be done to invert it, but it does have a unique inverse. What is shown here is the liner density for one simulation at 4 different representative times, as well as the surrogate generated form using the wavelet phase harmonics. That the same workflow was followed. We did have to go and use circular covariance rather than the normal covariance for the complex phase of the transformation. Also shown here to the right are lineouts going through the center of the image for both the original and the generated versions of it. And on the right-hand side is shown the magnetic field. One thing to note is that the things are well, and accurately generated by the surrogate model, including the relative orientation of the magnetic field of the two images in these cases. And now let me go and really get into the physics of what's happening and taking a closer look at these simulations and these surrogates. I call your attention here to the left at the principal components for the M=4 or quadrupole mode, as well as the M=2 dipole mode. You see for the quadrupole mode that it first of all has a quadrupole pattern in the first order transformation. Also, the strength of the quadrupole goes and decreases as the plasma starts to implode and eventually loses that quadrupole pattern as it goes to stagnation, and it also loses it as it goes, and it remains so as it goes through the expansion. This is also shown on the second order Mallat Scattering Transformation in terms of but now you'll go and see that it actually has 2 beats per sector for a quadrupole pattern, and this washes out as it goes and implodes to small radius. In this case, these are logarithmic radial plots in order to go and accentuate this decrease in the quadrupole mode. The opposite is true for the dipole mode. You see that it increases as it implodes, gets a very marked dipole character to it, and this persists through the expansion that we previously saw as this dumbbell character to the plasma. And this also persists on the second order Mallat scattering transformation, which has this low frequency dipole modulation to the 1 beat per sector character. Also, this goes and this character is enhanced as you go to a smaller radius and persists through the subsequent expansion. I now go and call your attention to the upper right-hand corner. This was gone and done for 3 different aspect ratios or accelerations, and also for 2 different adiabats, that a less aggressive and a more aggressive adiabat. I call your attention to the thinnest or the first pair to the thinnest liner and the first pair to converge. This is also, again, the evolution for the first principal component. I call your attention to the red and the yellow curves, that you see that there are few tie points for the MLP and the MLP that we're using here, the Multi Layer Perceptron neural network, is a universal function approximator, and it does it by a piecewise linear approximation. And so it has very few linear approximate points where it is flat. It has more where it changes more rapidly and puts one of the tie or approximation points at the point of maximum compression, the stagnation point, and also at the point of discontinuity. You also understand now why you need to use rectified linear units, because it is discontinuous. It has this cusp in the first derivative, and a rectified linear unit can go and follow that cusp, where if you used a continuous unit like a hyperbolic tangent, which was done up until the most recent renaissance of neural networks, which really was based on using rectified linear units. It goes and comes about because of the fact that it can go and sample it sparsely where it is roughly linear or slowly changing, and can actually go and have these cusps. Now you go and see that the higher adiabat, which is the red curve, goes and has more compression and also compresses first, where the other adiabat takes longer to go and compress. Then if you now go to the next aspect ratio, the thicker one shown by the green and magenta, that it goes and takes longer to compress, but things are still well followed. And then again for the thickest, the smallest aspect ratio, that takes the longer to compress, but things are still well represented there. I now call your attention to the permutation feature importance, that it should be no surprised that time is the most important thing to determine what is going on. So time is the most important feature. Then next is the aspect ratio. That makes a big difference in terms of the acceleration throughout all time. So it should be no surprise that it is the second most important. What is a bit interesting and goes and shows what is involved in the physics of what's going on is the fact that the next most important is the phase of the m equal 2 or dipole character. And what's happening here, as was displayed on the MST on the right, is that the energy is inverse cascading from the higher m values to the lower m values, forming a emergent behavior or a self-organized dumbbell m equal 2 character, and that the initial phase of the m equal 2 is being enhanced by the inverse cascade, so that the initial phase is very important to determine what the evolution is. Next is the size, okay, that is not as important because it's always going to go and inverse cascade and grow. And then the next one is the adiabat that you end up being on. That only matters in terms of the maximum compression, and so that it is not as important as the other factors. And because of the inverse cascade from the m equal 3 and 4 mode, those do not matter at all. There are many different structures. The most general is to separate the prediction into 3 phases. The first goes and takes the initial conditions into the initial fields in terms of a multi-layer perceptron surrogate. The second takes the initial fields, coupling constants, as well as time, does the dynamic mapping to the fields as a function of time. And finally, you have a synthetic generation surrogate that takes the fields as a function of time to what the synthetic diagnostics should be. You also can go and do this all at once, forming one surrogate that takes the initial conditions and coupling constants to the diagnostics. Here I've gone and indicated the dimensions of the input and output dimensions to all these MLPs. And the current work goes and takes the initial conditions and time to the time evolution of the fields. So it's kind of a hybrid partial composite for a partial combination of this decomposed approach of just the first two. Okay, now I'm going to spend a bit of time on this slide to really talk about what's going on here and why this went and worked so well, and go and really first of all, by introducing you to sort of the fully generalized and proper way to write this down in terms of the Heisenberg scattering transformation, or the generalization for this. There's good reason to choose the Heisenberg scattering transformation because this is really a canonical way, or a Heisenberg way, of looking at quantum field theory. But I'm not going to really talk too much about that as I go through this. And I call your attention first to the definition of this scattering transformation. First of all, we start with the field, or these images. We go and we take the complex logarithm of this field, And then we go and rotate it 90 degrees. And the R naught is going and changing the origin so that this is an identity map for small variations in the image. Then there is a convolutional, multi-layer convolutional network where each layer comes about from the product. The phi is the mother wavelet of the convolutional filter bank. The nonlinear rectifying function is this I log R naught. These are complex wavelets. This is a complex transformation. We are using the complex logarithm of it. Okay? And then finally, there is a pooling function, which is the father wavelet on the left-hand side of it. This can be also viewed as a Wigner-Weil transformation from the cotangent bundle space with a symplectic metric on it given by the fields, the images, and the associated covector momentum to it, to a complex Hamiltonian function that is analytic. Okay, this formally, mathematically, is a logarithmic generating functional, okay, of the complex Hamiltonian. But again, this can just be viewed as a specific form of a convolutional network, okay? And so that by the specific choice of this of the Heisenberg scattering transformation, we have picked one thing from this exceptionally large order of infinity Banach space of all possible functions. And that, for many uses of convolutional networks, first of all, a very restricted subset of structures end up being chosen, but then you still have to do an optimization in order to choose which convolutional network you are going to use, train the convolutional neural network, but you do this over many times hundreds of millions, if not a billion parameters, right? So it's a very hard, very time-consuming. There is no choice in this case. There is one logarithmic generating function of the complex Hamiltonian of the system, okay? And so this takes you from the Banach space down to a Hilbert space of all possible these functions of scale, okay? But what these actually are all possible renormalization functions, or all possible ways that the physics can go and change as a function of scale, okay? But it's complex scale, both direction as well as magnitude as well as phase. The dimension that we end up having on this is normally an infinite dimensional Hilbert space of all functions, but since we go and have 2D images that are discretely sampled, that you end up finding that you now go and have this as is going to be, in our case, 256 squared as a dimension of what this Hilbert space is. Since this is a logarithmic generating function, the equation for the evolution is going to be that the first derivative is equal to 0, or that you're going to be confined to a complex hyperplane, okay, or a low-dimensional Cn sub d, okay? And I'll talk a bit about what n sub d is, but you can think of it as just a few or a few dozen okay, in terms of what n sub d is, and that the evolution or the HSTs are going to be confined to a low dimensional subspace of this, okay, which you, from a machine learning viewpoint, you can view as a reduced order model, okay? And that what is sort of great about the fact that this is a logarithmic generating functional is that things are now linear. This is very similar to taking the log of the likelihood so that things will now be linear in the log likelihood. Okay, and again, now we go and use a principal components analysis that can very quickly find what this low dimensional linear subspace is. Okay, and now there's one part left to it, is that we want to go and find out what the Hamiltonian, this analytic function is on this low dimensional manifold, so that we're going to go and have, let's say, 7 numbers coming in here, and we're going to want to go and find the this and use this multi-layer perceptron neural network, which is a universal function approximator, to go and approximate this analytic function. Okay. Now, first of all, analytic functions are the maximally flat function that track out the geodesics, okay, on this manifold, or are equivalent to knowing what the topology is of the manifold. In other words, given the topology of the manifold, this analytic function h is the solution to the Laplace's equation given the boundary conditions, which are the topology of the manifold. Okay, and then this and so that this multi-layer perceptron, since it is a linear approximator, it will go and is very good at approximating a maximally flat function, but this maximally flat function will have singularities, and it will also be very good at mapping out and finding where those singularities are, or those cusps in the function. And now the group action or the motion, okay, or will be given, or the geodesic motion will be given by the contours of the real part of the complex Hamiltonian being a constant, and the interaction with external heat baths or the directions perpendicular to the Hamiltonian motion or geodesics will be given by the orthogonal set of curves in the ad direction or dh direction will be given by the imaginary part of h equaling a constant, okay? And so now let's talk a bit more about this dimension right here. It is well known that the number of renormalization solutions to the renormalization function will be the number of fields plus the number of coupling constants, or the way that this will go and couple to an external field. And so that you will now go for this case that we're dealing with, since we ended up going and you were dealing with resistive MHD equations. Those have 6 fields, which are the density, charge density, and 4 fields, okay? Since it's resistive, there will be one ad direction, so that this will now be 7-dimensional, okay? These are the solutions to the renormalization group equation. So that we start with going and finding out where we are in this Hilbert space. we find and take the PCA to find these n functions beta sub I, and the beta sub I are the solution to the renormalization group equations, and then those will then be the topology, or the complex Hamiltonian is found by the multi-layer perceptron. In this case, we do have dissipative motion, and so that will go and relax down to the ground states or equivalence classes of it, okay? And so now let's go and say let's say that we go to a two-dimensional manifold in this case, which has a toroidal topology, that you can go and see that there are two basis vectors associated with going around the whole of it or going around the waist of the torus, associated with beta naught and beta 1, and that you also see that there are two ground states or equivalence classes associated with going around the waist of it or going around the whole of the donut, or going around the waist of the donut, okay? And now let me just go and just talk about also, and these tend to be very low dimensional, 0, 1, 2 dimensional, normally at most. And so we've gone from this Banach space infinite by choosing the HST. The Hilbert space is n sub d, but then this n sub little d to the d, this n sub little d is 7 in our case, and this is probably just 1 or 2 dimensional in terms of n sub g, which is the dimension of the ground states of the attractor that you end up dealing with, right? And then one final thing is that things can be quantized, and that's called first quantization in terms of the group action H. But there can also be a second quantization of the way that this will go and interact with external heat baths, such as through dissipation, and lead to dissipation in terms of the add direction, and that is normally called second quantization. And this comes about from the fact that you are dealing with orbits, or that you have a complex space, and that you have a periodic variable, and that leads to the quantization of these fields. Okay, now let me go and get to the final discussions and conclusions. First of all, we've formed a fast, high-fidelity surrogate based off of resistive MHD. This has given a 10 to the 7th acceleration over the conventional finite volume calculation. Each one of the 539 simulations took approximately 360 core hours to do, and that this was in the surrogate in terms of the forward model. Once we have trained it, takes less than a tenth of a core second to do. This is a simple ML-DL architecture that is fast to train. It took 1 core second to do the principal components analysis, 20 core seconds to train the MLP, 16 to 24 GPU hours to do the MST or the WPH on the training data, and I've already discussed 200,000 core hours to generate the training data. This also gives the field-to-field correlation if the WPH is used. It has physically interpretable results with meaningful graphical displays, as I discussed in depth on that one slide. It gives fundamental insight into the physics, as I've just discussed on the previous slide, both in terms of nonlinear dynamics, physical kinetics, the quantization and second quantization, the renormalization, as well as the topology, all as I discussed on the previous slide. It's based on a transformation to a renormalization basis, where the dynamics is constrained to a low-dimensional linear subspace or reduced order model of a complex Hilbert space or manifold. These are the solutions to the renormalization group equations given by how the field scale as f, of which is the field, to the beta p with the basis vectors beta p that were found. This is a reduced order model in machine and deep learning parlance. A transformation, this is also a transformation from the cotangent bundle with symplectic metric to Cn with analyticity as the metric. This is a Wigner-Weil-like manifold safe transformation. The dynamics is now geodesic motion determined by the topology of the low-dimensional linear subspace or manifold spanned by the beta p. And by the way, the curvature of this manifold is given by the DHD betas, or the connection. The surrogate extrapolates well if new physics is not becoming significant. And that when I say new physics, that's not captured by the resistive MHD. Or in other words, just so that I'm going away, extrapolating away from the poles where the function becomes flatter, rather than extrapolating towards a pole where the analytic function h becomes more quickly varying, right? The surrogate can be combined with experimental measurement to test the causality hypothesis and to characterize additional causality if needed. And let me just take a couple moments to explain what's really happening here, or how this can be done, right? We can go and take experiments along and around a particular area and that are well captured with our resistive MHD simulations. We can now go and get new points that go to that extrapolate away, that go and scale away from where we have gone and tested before. We can predict with the resistive MHD what the answers should be. Now, if things get better, we are extrapolating away from the physics, right? The poles of the physics, and everything is good, and we have captured all of the causality. But if we go and notice that things are not being captured, we are sensing additional causality, and we can now go and ask the question, what are those vectors? Are there additional vectors? If there are additional vectors, there are additional terms that should be added to the partial differential equations of resistive magnetic hydrodynamics. And also, we will go and get from the data what those additional beta i's should be. And knowing what those spectrums are of the partial differential operator gives very, very large clues as to what the partial differential operator should be. Okay, and also if you find that you have the same number of beta sub i's, but some of them change, that in terms of the direction, that can give you an idea of how some of the terms should be modified. This is testing causality and also proposing what the additional causality should be. And finally, there is something that we really have learned about the physics of 2D MagLIF implosions. We have learned that it has an emergent behavior to a self-organized dipole dumbbell states This has been definitively demonstrated by the analysis shown here. I'd like to thank you for your attention. This is the end of the presentation.